so let's hop over here. Greetings, all. Hope everyone is doing well. Let's get these couple more students getting in. All right, let me go ahead and share my screen. Start the broadcast. So I will check. I'll check back on Zoom in about 12 minutes, just for any stragglers, people waiting in the waiting room, and to check the chat for questions and things of that nature. I hope everyone is doing well. Hope you all enjoyed your weekend. It was productive and restful. You know, you were able to do all the things you needed to do. Let me see. So this is what, College Algebra 1. So there's no lab component with this one, right? I think that's how we have it set up. So this is the top of week 3. So let me see, I think the first week we did, well, it was really orientation, but then week 2, we did 1.1 and 1.2. So this week, we're only going to focus on section 1.3. I think we're pretty much up to speed. We're going to be doing one section a week. And what that means is that next week, we have exam 1. I think I scheduled it to become available on this upcoming Sunday at 11:11 a.m. So you can start then. But in order to access the exam, I think I created prerequisites. I set some prerequisites where you need to pass the corresponding quizzes, right? So the quizzes for weeks 1, 2, and 3, you have to pass those. I think it's like, it should be 5 questions, so you have to get 4 out of the 5 correct in order to access the exam. Otherwise, the longer it takes you to access the exam, the less time you have to get full credit, and then the harder it is to get above 90, right? You can get a 90 all the way up to the very end of the semester on any assignment, but if you want full credit, it has to be submitted before the due date, okay? As usual, if you have questions, feel free to either unmute yourself to get my attention or type it in the chat. I do check the chat periodically. And this is remote online asynchronous. So basically all I need from you all from each session is to get your attendance credit, which you've already gotten for today. Once you get into the Zoom, you've gotten your attendance credit. So you're not obligated to stay. I do live stream these sessions onto my YouTube channel. And the idea is for this time to be used as like a Q&A study session or office hours. What I've been doing in the past is, like, for the classes that meet twice a week, on Mondays, I'll take some time to go through the lecture as best I can. That's why I went on and took time to make full recordings for the full section that's available on YouTube. And then on Wednesdays, I use that time to go through as many homework questions as I can. But we can do some of that stuff on today as well, just because we have a limited time to be around each other, to have access to each other. But I fill it with this other stuff just for the sake of filling it. Okay, so on that note, so let's continue chapter 1 on graphs and functions, where today we'd like to take a look at section 1.3 functions. And so some objectives here: we like to use functional notation and find function values. We like to find the domain of a function. We like to identify the graph of a function. We like to get information about a function from its graph and solve applied problems using functions, okay? So definitions, we have a special relationship such as y equals 10x, in which each element of x in one set, there corresponds a unique element y in another set. It's called a function. Y is sometimes referred to as a dependent variable and x is an independent variable. So, functions, basically you have a set of input values. It's usually independent. You choose it for whatever you want it to be. You pass it through the function and it'll generate a set of output values that corresponds to each input. So that's typically how we have functions. So a function from a set x to a set y is a relation in which each element x corresponds to one and only one element in y. All right.
Professor, I don't mean to interrupt your lesson. You said this is on you live streaming this as well on YouTube, right?
Yeah.
Okay, thank you.
Yep. Let me see. Set x to a set y. Let me see. So the set x is the domain of the function, and the set of those elements of y that correspond or assigned to the elements of x is the range, right? So what this means is like your domain is just going to be your collection of all your input values, right? And then you pass these inputs to your function, and then the range is the set of all the outputs, right? And then for it to be a function, each x corresponds to exactly one y. We don't have one x value corresponding to more than one y value, all right? So let's see it in action. So for each x in the domain of f that corresponds to unique y in the range, in other words, every x corresponds to one and only one y, the number y is denoted by f of x, read as f of x or f at x. We call f of x the value of f at the number x and say that f assigns the value f of x value to x, right? This is just some of the nomenclature. So, one of the ways, like in the past, sometimes students will see this and they'll think it means f times x, right? We're not multiplying by x. This is the function f of x or the function f evaluated at the value of x, right? So this statement here is just to remove, like, to minimize the chance of you. Sometimes students try to multiply by x, and that's not what that means here, right? This means the function evaluated at the value of x. Okay. So functions can be defined by ordered pairs, tables and graphs, or equations. Okay, you are messing up. All right, let me back out. And we are working here. Cool. Yeah, so we're here. So determine whether each relation defines a function, right? So it's not a function if you have repeating x's. That's a simple way, right? If you have one x that corresponds to more than one y, then it's not a function. Just like in life, you don't want to repeat your x's. You know, it's usually not a good idea. So then the same thing here, right? So it's just a silly way I have to remember this, right? So if we look at part A, is this a function, yes or no? In other words, do we have any repeating x's for part A? Are there any repeating x's?
Yes.
All right. Which one?
Negative one.
Right. So if we were to plot this, when x is -1, you're telling me the y value is 2, and also when x is -1, the y value is 3. So then this is an example of something that's not a function, a relation that's not a function, because you have one x value that has two different y values. If we were looking at the graph, this is an example of something that would fail the vertical line test. If you can draw a vertical line and it touches your graph more than once, then it's not a function, right? So these 2 points will be stacked on top of each other. And so for that reason, it's not a function. In part B, are there any repeating x's? Notice there are no repeating x's, right? So then every x corresponds to a unique y. Now we have repeating y's, that's okay, but you don't want to have repeating x's, right? So then part B is an example, is a function. Oh, and then the domain of part A is basically your set of inputs. So it's -1, 1, and 5. You see it here. And then the range is a set of outputs, which is 2, 3, and -3. Okay. Again, this is not a function because two ordered pairs have the same first component. In other words, they have repeating x's for part A. And then the domain for part B, we have the -2, 0, 2, and -1. That's the domain, the set of inputs. The range of our set of outputs, 1, 2, and -3. And B is a function. So we see our domain, we see our range. The relation is a function because no two ordered pairs have the same first component. Okay. Let's kind of keep going for another 5 more minutes. Determine whether y is a function of x for each equation. Okay, so for part A, is that a 2 or a 3? Part A has a typo. 3y, okay. So this was supposed to be -3y. Okay. So for instance, for something like this, for part A, if we wanted to determine whether whether y is a function of x for each x in each equation, let's go ahead and solve for y in part A. All right, let's solve for y. So we're starting with this 6x squared minus 3y equals 12, right? Okay, I want to add the 3y and subtract 12. I'm just going to do it in one go. So I'm going to add 3y to both sides. And if I subtract 12, I'm going to get 6x squared minus 12, right? So what I did, I moved the 3y this way using the inverse operation. I moved the 12 this way using the inverse operation. Then I just switched the left-hand side and the right-hand side. So it looks like this, because I just wanted my y on the left. Okay. And then if we want to isolate the y, use the inverse operation to move the 3, right? So if we're saying 3 times y, then the inverse operation is division. So we're going to divide both sides by 3. In other words, we can divide each term by 3. Terms are things that we add and subtract, right? So if we divide each term by 3, we're going to get, in this case, we would get y equals 2x squared, what is that, minus 4? Okay, so then now to determine, so if we get y equals something like this, notice that from here, I would just look at the graph, right? One way that you all can look at the graph, you can make a table, like choose different values of x, find the corresponding y values, and plot the points, right? You can also, let me see if I can just type it. So if you had like a graphing utility, this is a TI-83 plus ROM. Another site where you can like do free graphs is GeoGebra, and I know students have also used Desmos. If you just go to Google and type in free online graphing, like mathematical graphing, you know, I've used GeoGebra, and I know students have used I think it's Desmos in the past, right? So, you know, if we went to y equals, I mean, we can just do it here. So if we go to our y equals and type in 2x squared, right, minus 4, we could just look at the graph, right? I think it's now we're going to discuss, you know, oh, the highest x1 is a 2, so we would know that's a parabola. It's a U-shaped curve. This negative 4 means that actually we might need to change the form. Yeah, I think negative 4 is fine. The y-intercept is negative 4. It's the U-shaped graph that opens upward, right? So let's look at it. I'm going to hit graph, and this is just a standard window. Notice the y-intercept is negative 4. It's a U-shaped graph that opens upward. So no matter what x value you choose, there's one unique corresponding y. Every x corresponds to exactly one y. This is an example of something that would pass the vertical line test. What that means is no matter where you place the vertical line, it'll touch the graph once. So then for part A, is y a function of s? Is y a function of x? We would say yes. Yes, it's a function. And let me see. I'm not sure if this is my first one somewhere. Can I paste? No. Okay. All right. And just stop me. I know I'm talking a little bit fast, but you know, this is live stream. You can always like pull it back and later and look at it, you know, and like you can change the speed and pause and rewind and do everything you need to do. So for part B, if we want to determine whether y is a function of x, right? Let's do the same thing. Let's solve for y. So in part B, we're starting with y squared minus x squared equals 4. Add the x squared to both sides. So then we'll get y squared equals x squared plus 4. If we want to solve for y, if we have to the power, if we have y squared, the inverse operation, if we have y squared, the inverse operation is going to be square root. Can somebody tell me, whenever we take the square root, what symbol do we need to include? Or even root? Yeah, whenever we take square root, what symbol do we need to include?
Plus or minus.
Plus or minus, right? Plus or minus. So because of the plus or minus, Then we get y equals basically what you see there, plus or minus this guy. So for instance, say we let x were 1. Notice that when x is 1, we get 2 different y values. We get plus or minus the square root of 5, right? So we have 1x, we have several, all the x's correspond to more than one y. So this is an example of something that is not a function, right? You have one x, you have an x that corresponds to more than one y. If we were to look at the graph of this is an example of something that would fail the vertical line test, right? So we're going to say not a function. And let's actually see how we can look at the graph. Let's copy, paste. So say we got something like this. I mean, once you see that plus or minus, and if you're talking about functions, that's a dead giveaway right there, right? So if we wanted to just look at the graph just for the sake of doing it, first I'm going to put in 2, right? So the first one's going to be the positive square root. So then we have x squared plus 4. And then in the second slot, we're going to do the negative square root of x squared plus 4. So what this should be, this will be, not only will it be the top half of a sideways parabola, but it'll also be the bottom half of a sideways parabola, right? So then if we go to graph, oh, maybe not. Oh yeah, sorry. I'm thinking when we don't have the x squared term, it would be the parabola. But in any case, it's still not a function because we can basically, this is an example of something that fails the vertical line test. You can draw a vertical line and it'll touch the graph more than once, right? Again, the sideways parabola would be if that square were not there, but I forgot that it's there. So we get an image like this, right? But again, this image is an example of something that fails the vertical line test. So we can draw a vertical line, it'll touch our graph more than once. So then it's not a function. In other words, you have one x that corresponds to more than one y. You have at least one. And here we have some type notes of what we just experienced, right? So again, we mentioned that typo there. And then when you solve for y, you get something like this. So every one value of y corresponds to each value of x. So this defines y as a function of x, right? Basically passes the vertical line test. And then here, when we solve for y, again, we get that plus or minus. So then 2 values of x correspond to each value, 2 values of y correspond to each value of x. So then y is not a function of x, right? Okay, let me see my time. Let me check Zoom really quickly for any stragglers. Okay, so I'm gonna stop sharing my screen for a moment. Try to get these guys. That's okay. This one. Okay. This one. Oh, let's see. This one. It's elementary. Oh, I missed somebody. Okay, let me see. I don't think I saw that name. I think I got everybody. Yeah, I think I'm just missing the one student. Okay. And I don't recall seeing that name. Okay. All right, and let me check the chat really quickly. So a question pops up. It said, do we get only one attempt at the exam or multiple attempts? So I think I got the student already. We get unlimited attempts at all assignments. So you can take the exam, take some notes. Okay, let's talk about the exam a little bit more. Get to the next slide. We finished that one. Let me just kind of go like this for a moment. Come on. Come on. All right. no. We're at the 2 o'clock. There we go. I had to like reboot it. Okay. Just trying to get some white space. Okay. So there was a question about the exam. Do we only get one attempt? We get unlimited attempts at all assignments, including exams. The system is set to take our highest score. And you can work on any assignments, including exams, past the due date with only a 10% late penalty, right? It says if you're really trying to go for above a 90, then you want to try to submit it on time. If you're indifferent about getting above a 90, you can submit it late. Unlimited attempts. The system is set to take your highest score. Also with the exam, each time you take it, the questions are going to change. It's not that I'm shifting the questions around. It's a pool, so it's going to be a completely different set of questions. But it's the same content, right? I think I scheduled the exam to become available this upcoming Sunday morning at 11 a.m. And then it'll be due the following Sunday night, like a week later, at 11:59 p.m. Right, so that's pretty much midnight going into Monday morning. Okay, so that was a good question in the exam, and now she's kind of behaving a lot better. She's still a little bit temperamental. There we go. I think we finished that one, so we left off here. Well, let's see. So in this example, it says let G be the function defined by this equation, and we're asked to evaluate these functions, right? So for instance, like part A is saying basically let X be 3. So, it would be like 3 squared minus 6 times 3 plus 8. Let me see, that's a 9 minus 18 is negative 9. So it looks like the result there is negative 1. You can plug that in, write it out. I just want to do a showcase on how we can do this in the calculator. Okay, so for my y equals, I'm going to type in x squared minus 6x plus 8. Okay, and I quit. I went back to the home screen, and then on the right hand side of the calculator in the center, you see this button that says clear. To the left of that button is a button that says VARS. I think that's short for variables. I'm going to click on that button. I'm going to go to the right for y variables. And I'm going to click on number 1 for our functions, and then number 1 again to call on the function that we just typed in. So then now, when x is 3, I can get it to output. I think we got negative 1. All right. I'm going to hit second enter to recall what I just typed. Now, when x is negative 2, if we do a quick calculation, negative 2 squared is going to be what? A positive 4. Negative 6 times negative 2 is a positive 12. So that puts us at 16 plus 8 puts us at 24. All right. So when x is negative 2, we should get a result. I think we said 24. And then when x is a half, I think it was like 5 1/4. So I'm going to do 1 over 2. See the 5 1/4 there. All right. So at least, for evaluating numbers, I just did a demo on how you could type in a function into your y equals and then evaluate it at specific values. You can also look at the table. And then for parts D and E, we would have to replace each x with that binomial expression, expanded, simplified. Let's go ahead and walk through that one actually. So then say we were working on part D. So then G of a plus 2, basically we're replacing each x with a plus 2. So I'm going to say x squared minus 6x plus 8. And again, we're replacing each x with a plus 2. A plus 2, right? So notice the first thing I did was I replaced each x with a blank set of parentheses. And then what went into the blank parentheses? This guy right here, right? So then we just want to expand it, combine like terms, and simplify. So then FOIL, first, outer, inner, last, we're going to get a squared plus 4a plus 4, right? If you combine like terms. Distribute the negative 6, we're going to get negative 6a minus 12 plus 8. Combine like terms. we get a squared. 4a minus 6a is a negative 2a. 4 plus 8 is 12, minus 12, they cancel out. Am I missing something? Mm-hmm. 6a minus 12. Okay, I think this is okay. Let's see, can I paste? And then it's something similar for part B. For part E, I'm going to rely on my prepared notes for that part just because it gets a little bit messy. Okay, so for part A, you see the -1, 24, and this is 5 1/4. All right. And we can also do, if I do math as a fraction, it's going to take that answer and convert it to an improper fraction. So 21/4, right? And you can see the same thing. And then I think we got a squared plus a for part plus minus 2a. I'm just saying stuff, right? We got a squared minus 2a. You see it here. And then the last one was worked in a similar fashion as part D, but then it ends up looking something like this. Part E is like a precursor to something that's coming up that we use in like a lot of different courses. So the agreement in the domain, can I get somebody to read this slide for me, please?
If the domain of a function that is defined by an equation is not explicitly specified, then we can take the domain of the function to be the largest set of real numbers that result in real numbers as outputs.
All right, thank you for that. So what this is saying, basically, for unless the domain is specified, our domain is going to be the largest set of real numbers that correspond to that have real outputs, right? We don't want to consider real numbers as going to have non-real outputs. So that's unless the domain is already specified. If it's not specified, we take the largest set that produces real outputs, right? So for instance, okay, with this one, we're asked to find the domain of each function. So there's two main functions at play here, right? The first one is the rational function. It's basically like a fraction. And then the second one is the radical function, which is like a square root, an even root, right? With the rational functions, when it comes to fractions, what's the number that we have to be on the lookout for? We cannot do what when it comes to fractions? When it comes to the denominator. What do you think is a special number? Like whenever we're working with fractions, we cannot do what, where?
You can't have a 0 in the denominator.
Right. We cannot divide by 0. We cannot have a 0 in the denominator. So whenever we have rational functions, basically it looks like a fraction, we cannot divide by 0. So what we'd have to do is find the value of x that makes the denominator 0, right? And so we do it in the following way. If we want to know what value of x makes the denominator 0, then just set the denominator equal to 0 and solve. So I think if we add x squared on both sides, we'll get x squared equals 1. If we take the square root, x equals plus or minus 1. All right. So what we're saying is that if we plug in 1 or -1 into this original function, it makes a 0 in the denominator. So we have to throw out x equal to 1 and -1, right? So let me put, hey, x cannot be 1 and -1, right? So the domain for part A is going to be all reals except 1 and -1. And then to capture that in interval notation, if we want everything except 1 and -1, the far left is going to be -infinity up to -1. And then we want to exclude -1, and then we want to go capture everything from -1 to 1, and then from 1 to infinity. All right. Can anybody tell me what grouping symbol does infinity always get in this context? So infinity always gets parentheses, right? Because we do not want to include 1 and -1, these also get parentheses. And then the solution set, we're basically combine the first set with the second with the third. So we combine them with a union, right? And again, in this context, parentheses means we get really, really close. We get really close to these numbers, but we don't include those numbers themselves. Again, we never reach infinity. That's why they get parentheses. We never reach infinity. Right? Okay. So again, to recap, when we're working with a rational function, we cannot divide by 0. So we want to find what values of x make the denominator 0 by setting the denominator equal to 0 solve. Okay. And then for part B, the other type of function is the radical function, right? What kind of numbers can we not take the square root of? What kind of numbers can we not take the square root of? So some examples of perfect squares, for instance, the square root of 0 is 0. The square root of 1 is 1. The square root of what? 4 is 2. Square root of 9 is 3, so on and so on. Can you think of can you give me an example of something that we cannot take the square root of? To get a real answer? Now, obviously, we can do like square root of 5, but then it's going to be irrational. It's still real, but it's just going to be some long decimal. So notice how like the square root of 9 was 3 because 9 is 3 times 3. The square root of 16 is 4 because 16 is 4 times 4, right? So then what if we try to do like the square root of -1, right? Notice that like negative numbers, we don't have a number where when you multiply it by itself to give us a negative. Because if you say -1 times -1, that's +1. If you say +1 times +1, that's also +1. So long story short, we cannot take the square root of negative numbers, right? So those are the two main pieces of information here. We can't divide by 0, and we can't take the square root of negative numbers, right? We have to throw out any x that makes the denominator 0. We have to get rid of any x that makes the radicand negative, right? So if this inside part, i.e. the radicand, can't be negative, it needs to be non-negative. In other words, this inside part needs to be greater than or equal to 0, right? Okay, hopefully that wasn't too terribly bad. So then for part B, long story short, we can't take the square root of negatives, so the radicand needs to be greater than or equal to 0. In interval notation, we're talking about all the numbers that go from 0, that's basically going to the right of 0. Infinity always gets parentheses because we never reach it. Because we have that bar here, can you tell me what kind of grouping symbol the 0 might get? So because we have this, yes.
A bracket.
Right? So because of this bar, that means that we can be equal to 0, so then the 0 will get a square bracket. So to kind of recap, parentheses means we get really, really close to that number, but we do not include that number. A bracket means we get really, really close to that number, and we do include that number, right? That's the difference between this symbol and this symbol. Or actually this symbol and this symbol, right? One means you get really close, but you don't include the number. The other means you get really close and you do include the number. And mathematics, it gets into a lot of like very subtle, very like precise to the T concepts like that, where oftentimes I've noticed that, okay, exactly on this number, what happens? Okay, and then slightly to the side, one way or another, what happens, right? And a lot of mathematics deals with that. What happens exactly on the mark and what happens when you're close to the mark. A lot of the concepts, and it's very subtle, but that's what a lot of mathematics like boils down to, either being on the money or very close, right? And so then once you have a sense of what happens exactly on that number and what happens close to that number, because very, very drastically different things can happen when you're on the money and when you're close, right? That's like saying, man, I was this close to winning $1 trillion, right? I mean, it's if you're close, that's great, but if you didn't win, you're not on the mark. You missed the mark, right? That's a huge difference between being close to winning $1 million or $1 trillion or whatever, and actually winning or earning the money or whatever. You see what I'm saying? So, long story short, mathematics boils down to that oftentimes. What happens on the money, and then what happens when you're close to the target, right? That's what a lot of the conversation boils down to. So we went through the first two examples. This third example, what it does, it fuses those two concepts together. Not only can we not divide by 0, but we can't take the square root of a negative, right? So if we consider the square root by itself, then the radicand would need to be greater than or equal to 0. But because we can't divide by 0, we can't allow it to be equal to 0. So now we say this radicand has to be strictly bigger than 0. And then similar here, we can't take the square root of negatives. So this guy has to be greater than or equal to 0, right? So we have some typed up notes for that already. So what value of x makes the denominator 0? Plus or minus 1. So then the domain is going to be, this is red, the set of all x such that x is not equal to -1 and x is not equal to -1. All right, let's read that one more time. The domain is the set of all x such that x is not equal to -1 and x is not equal to 1. Okay, this vertical bar just means such that, right? So basically this is saying everything except 1 and -1, and then this is an interval notation, right? We kind of went through that. For part B, we said we can't take the square root of negatives, so the domain is the set of all x such that x is greater than or equal to 0, and here it is in interval notation. Okay. This one, the square root of a negative number is not a real number, so then usually the inside part here has to be greater than or equal to 0, but because it's in the denominator, since the denominator cannot be 0, instead of it being x is greater than or equal to 1, you have to remove that bar, right? It cannot be equal to 0, so it can't be equal to 1. So then here the domain is x is strictly greater than 1. So then the domain is the set of all x such that x is strictly greater than 1. And we're talking about basically all the numbers to the right of 1 will work. Anything 1 and to the left is going to make this undefined. Okay, I'm totally faded. Let me see. And then this one, the radicand, the inside part has to be greater than or equal to 0. Oh, this one. So to solve when the inequality, it's a little bit convoluted. When the inequality is greater than or equal to 0, the simplest way I could think, if you graph just this inside part, you're looking at this parabola, if this has to be greater than or equal to 0, you're also saying, when is this graph above the x-axis, right? If this has to be greater than or equal to 0, another way of visualizing that is when is this above the x-axis, right? So we could find the x-intercepts and then choose test values. For instance, I think the x-intercepts are -3 and 1. 9 minus 6, yeah, right? So when you're looking at the graph, right, positive x, here, this is going to be a quick sketch. So say the positive x is in this direction. The graph is going to be something like this, right? I'm saying that my x-intercept is -3. My other one is 1, right? So if this has to be greater than or equal to 0, we're talking about this guy and this guy. So what are the corresponding x's for where it's above? You know, so once you identify the x-intercepts, you basically choose test points. If you choose something left of -3, it should make it true. If you choose something between -3 and 1, it should make it false. if you choose something to the right of 1, it should make it true. And because it can be equal to 0, we would include square brackets here, right? I know that's kind of glossed over. Just do the best you can with that. Because of like these kind of things, these concepts, how subtle they are and precise and like, on the money. Because the concepts can be very subtle, this is why I encourage you to like work together, to link up with the tutors. Get what you can from me. I know that hearing me drone on about this day in and day out, it gets old fast. I get it. But you got to get it from somewhere if you can't get it from me, right? And as long as you get it from somewhere, that's my request. If you're not going to get it from me, just make sure that your source is like it's a sound source. They know what they're talking about. They're not leading you astray. You can get what you need out of it, and then just do at least if you do the minimum what I require, you should be okay, right? All right. So I think I'm kind of spent. I still have, what is this, 3? I still got like 2 more classes. I'm totally burnt. Usually with them, I just to give myself some energy, I just go ahead and kind of work through the homework. I'm not sure about top of cover window. Okay. I might, I don't know. I'll figure something out with that. But with that, we're going to end the session here. Are there any questions? Did you guys have any burning questions? So I do intend, I know I said this last week, I do intend to make, I want to preload a student version of these notes. So basically it'll be the same notes but when we get to the examples, it'll be the question without any supporting detail. And then every time we make our way through a lecture, I'll load the instructor version where it'll have all the details that's missing. And so once you have the notes in advance, I would encourage you to like look at them in advance, try and attempt the example. See, can you get to those conclusions before we go through it together? And then, the more you can do on your own and ahead of time, the better. But let me check the chat one more time. I can. Man, all my stuff is kind of on the fritz. There we go. Okay, the chat looks clear. If there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Okay, guys, take care. I'll see you Wednesday, same time, same place. Take care. Peace.
You as well.
Have a good day.
Thank you. Have a good one.
Thank you, Professor.
Yep. All right, let's go. Stop.